We typically obtain data from two distinct sources, experimental and observational studies. In an experiment, researchers actively intervene by applying a treatment and observe its effects on individuals. In an observational study, researchers observe and measure characteristics without attempting to modify the individuals being studied. For example, in the experimental study, we will conduct an experiment with one group treated with ice cream while another group gets no ice cream, and then we compare the drowning rates between the two groups. If the experiment was properly designed, it will show that ice cream consumption has no effect on drownings. In the observational study, researchers will observe the past data on ice cream sales and drowning rates and notice a correlation between increased ice cream sales and a higher rate of drownings. However, this type of study can lead to misleading conclusions. In this case, the researchers failed to account for the lurking variable of temperature. Warmer weather drives both higher ice cream sales and more swimming activity, which increases drowning risk. A well-designed experiment includes the following key elements. The first one is replication, which ensures reliability by repeating the experiment on multiple individuals. For example, if we're testing a new painkiller, we won't give it just to one person. Instead, we will test it on hundreds or thousands of individuals to account for differences in age, gender, and health conditions. The second key element is blinding, which minimizes bias by preventing subjects from knowing whether they're receiving the actual treatment or a placebo. This helps reduce the placebo effect, where individuals feel better simply because they think they're being treated. For example, in a drug trial, participants will not know whether they're receiving the real drug or a sugar pill. For the double blinding, it takes this step further by ensuring neither the subjects nor the researchers know who is receiving the treatment or placebo. This eliminates bias from researchers who might unconsciously influence the results. For example, if a doctor knows a patient is receiving the real drug, they might accidentally give more attention or encouragement to that patient, affecting the outcome. And the last key element is the randomization, which ensures fairness by randomly assigning subjects to treatment or control groups. This prevents groups from being unintentionally biased. For example, when testing a weight loss program, researchers randomly assign participants to either the program group or a no program group, ensuring factors like age or activity level are evenly distributed. There are three main types of observational studies. The first one is retrospective studies, also known as case control studies, where these studies examine past data to identify potential causes or contributing factors for a particular outcome. For example, looking at medical records of patients who developed lung cancer and comparing their smoking history to those who didn't, it's a retrospective study. For the cross-sectional studies, the data is collected from a group of subjects at a single point in time. These studies are often used to measure prevalence or associations at a specific moment. For example, conducting a survey to find out how many people in a community are currently smokers and their health status is a cross-sectional study. For the prospective studies, also called longitudinal or cohort studies, researchers follow a group of subjects over an extended period to observe how certain factors influence outcomes. For example, tracking a group of non-smokers and smokers over 10 years to see who develops lung disease is a prospective study. These three study types differ in terms of when the data is collected: past, present, or future. It is important to note that while observational studies can provide valuable insights, they are limited in their ability to establish cause and effect relationships. That's because these studies cannot control for all potential confounding variables. Confounding occurs when the effects of multiple factors are intertwined, making it difficult to isolate the specific cause of an observed effect.